Welcome back. Last time we considered that a vector is a physical quantity, so that if two different observers are looking at that vector using different frames of reference, then the difference between the components that they measure for that vector must be able to be obtained if you know the difference between their frames of reference. Specifically, if we had two observers using two different right-handed rectangular Cartesian frames of reference, then they would have two different orthonormal bases, which we label EI bar and EJ. And therefore, if we find the transformation that converts EJ to EI bar, we should be able to convert the components of the vector as seen by the observer using one frame to the observer using the other frame. And what we further went on to show is that given that these two frames of reference are orthonormal, they're both Cartesian with unit orthogonal base vectors, and they both have the same handedness, then the transformation from EJ to EI bar would be a proper orthogonal matrix. In other words, it would be a rotation. And therefore we could write that EI bar is equal to Mij times Ej, where Mij is a matrix of angle cosines, and therefore Mik times Mjk equals delta Ij. In other words, M is an orthogonal matrix, or M by M transpose is equal to I. So if M is a rotation that takes you from Ej to EI bar, then M transpose would be the inverse rotation that takes EI bar back to Ej. And as we showed last time, the components of this matrix are just the angle cosines, the cosine of theta Ij between each of the three base vectors in one coordinate frame and each of the three base vectors in the other coordinate frame. So now that we can transform from one frame of reference to another, we must be able to find the components of a vector A in the new frame of reference, given its components in the original frame of reference, using that transformation. So the vector A has components AI bar in EI bar and AJ in EJ, and therefore equals Aj by Mij times EI bar. In other words, the components of the vector in the two frames of reference are related by M, so Ai bar equals Mij times Aj. And similarly, Ai equals Mji, Aj bar, where Mji is the transpose of Mij, and therefore the inverse since it's orthogonal. Or in matrix notation, A bar, the components of A in the new coordinate frame, is equal to M by A, and A is equal to M transpose by A bar. So, for example, let's show using this orthogonal transformation that the dot product A dot B is independent of the coordinate frame. In other words, we're going to show that regardless of which coordinate frame we use to take the dot product between two vectors, we get the same result. And actually, and that's important because it suggests that the dot product between two vectors is also a physical quantity, since the vector is a physical quantity. So A dot B in the new frame of reference would be Ai bar, Bi bar. Converting that to the original frame of reference would be Mij, Aj, Mik, Bk. But Mij, Mik is delta Jk, so that gives us delta Jk, Aj, Bk, which is Aj, Bj, or if you prefer, Ai, Bi. In other words, Ai bar, Bi bar is the same as Ai, Bi. So, as another exercise, you can do the same thing yourself for the vector product, A cross B. So if A is a physical quantity and B is a physical quantity, then you'll be able to show that the cross product is also a physical quantity, and therefore regardless of which frame of reference you use to calculate it, you'll get the same vector. So now let's move on to a new notation, which is the tensor or dyadic product. So again, the name tensor product refers to the result of the operation. The name dyadic refers to the operator. So we've said before that a tensor is defined by two vectors. For example, the stress tensor is defined by the traction vector t, which has units of force per unit area, and a unit normal vector n, which is dimensionless. We'll be introduced to other tensors as the course goes on. And just as there are vector operations between two vectors that yield scalars, in the case of the dot product, or vectors in the case of the cross product, the dyadic product yields a tensor. So here the tensor C, the rank 2 tensor C, is equal to the dyadic product of the vector A, dyadic B. In index notation, this would be Cij equals AI Bj, or in matrix notation, C equals A by B transpose. In other words, a 3 by 1 matrix by a 1 by 3 matrix gives a 3 by 3 matrix. So we could write this as A dyadic B equals AI EI dyadic Bj Ej, which would then be AI Bj by EI dyadic Ej. And so this product of the unit vectors, this dyadic product or tensor product of the unit vectors, are called the unit dyads. So there's actually 9 of these for each possible combination of I and j of these unit dyads. And in the special case, when we take EI by dyadic EI, we get I, the identity matrix, or identity tensor. We can also show that A dyadic B transforms one vector V to a new vector, which is B dot V by A. So that's a scalar times A, which is a new vector. And to prove this, let's take A dyadic B dotted with V. That would be AI Bj Bj times EI, which would therefore be equal to A by B dot V, since the Bj Bj would be the dot product of B and V. So we can see from this that the dyadic product is not commutative. In other words, in general, A dyadic B is not equal to B dyadic A. Now, equation 1 above must be independent of the choice of coordinate system. So just like we did for vectors, we should be able to write the components of the tensor in a new frame of reference and convert from one frame to the other frame using the rotation that takes us from one frame to the next. So for example, let's now rewrite A dyadic B in components of a new frame of reference, EI bar. So therefore AI Bj bar, EI bar dyadic Ej bar is MIP AP MJQ BQ, converting the components, and now converting the base vectors, MIR ER dyadic MJS ES. And now collecting all the M's, we get MIP MJQ MIR MJS AP BQ by ER dyadic ES. And now we can see that MIP MIR gives us delta PR, and MJQ MJS gives you delta QS. And then delta PR converts AP to AR, delta QS converts BQ to BS, and we therefore get AR BS. by ER dyadic ES, or changing dummy indices vector I and J, AI BJ by EI dyadic EJ. So now we've shown that AI bar BJ by EI bar dyadic EJ bar is equal to AI BJ by EI dyadic EJ. So you can see that this tensor operation is preserved when we change coordinates. Now, we don't have to stop at rank 2 tensors. We could define a rank 3 tensor by 3 vectors by taking the dyadic products of A, dyadic B, dyadic C, and then you would get AI BJ CK times EI dyadic EJ dyadic EK. So this would be a 3 by 3 by 3 matrix or a rank 3 tensor. We'll occasionally encounter higher order tensors, but most of the time we're working on second order tensors. So a second order Cartesian tensor A has components Aij, EI dyadic EJ, and in a different frame of reference, those components Aij bar would be referred to EI bar dyadic EJ bar. And so we can now expand this, again using the orthogonal rotation of matrix cosines, and we'll then be able to show that Aij MPI MQJ would be equal to APQ bar, or in matrix notation, defining APQ bar as the matrix A bar and Aij as the matrix A. Then we get A bar is equal to M, A, M transpose. And the inverse A is equal to M transpose A bar M. So this is the equivalent application of the orthogonal rotation M to a tensor instead of to a vector. So now we use M twice instead of once. And we've actually seen a transformation of this kind before. This is the same form as the spectral decomposition, and transformations of this kind are called symmetry transformations. That's because one of the properties of this type of transformation is that it always preserves the symmetry of a matrix. If A is symmetric, then A bar will be symmetric. If A bar is symmetric, then A will be symmetric. In the spectral decomposition, the matrix P, whose columns were the eigenvectors, is a special case of M. It is also orthogonal. It's the orthogonal matrix that rotates the coordinates into principal axes, which are defined by the eigenvectors, provided that the tensor A, or the matrix of its components, is symmetric. We mentioned a third order tensor could be obtained by taking the dyadic product of 3 vectors, and so the components of the third order tensor B would be Bijk, EI dyadic EJ, dyadic EK, and then in a different frame of reference, EI bar, they would be Bijk bar by EI bar, dyadic EJ bar, dyadic EK, etc. So the properties that we've talked about for defining second order tensors can be extended to third order and above. Now let's consider some specific properties of second order tensors that are properties we've seen before in the context of matrices. So the first one is symmetry. So in the same way that a matrix is symmetric, a tensor is symmetric if the matrix of its components is symmetric. In other words, if A equals A transpose, and hence the components Aij are equal to Aji. So this is a property not only of the matrix, but of all matrices that can be obtained to represent A, which means that symmetry is actually a property of a tensor, not just a property of a matrix, and thus we can write that A is equal to A transpose. It's a property of the tensor, and that's a symmetric tensor. And similarly, we can have a skew tensor or antisymmetric tensor in which A is equal to minus A transpose. In other words, if the components of A are symmetric in one frame, they're symmetric in all frames. If they're skew in one frame, they're skew in all frames. And as a result, it's really a property of a tensor. It's not just a property of a matrix. And we can similarly decompose a tensor into symmetric and antisymmetric or skew parts by taking 1/2 of A plus A transpose, which would therefore always be symmetric, plus 1/2 of A minus A transpose, that would therefore always be antisymmetric. And these operations are sometimes called sim A and skew A. So any tensor can be decomposed into a symmetric part and a skew part. Of course, if the tensor was symmetric, the skew part would be 0. I've posted a handout on TED summarizing tensor index and matrix notations for you to review.